I'll be presenting on successful sensitive blasting using SkyChrome, one of the projects we're involved in as a case study. Just to kick off the presentation, I'll first start with the agenda and purpose of this presentation, which is to provide insight into the process we follow at SkyChrome to successfully blast in extremely sensitive areas without exceeding the allowable legal limits on nuisance factors and without unnecessarily sacrificing on the fragmentation quality. So the presentation will go as follows. We'll go into the introductions, and then we'll go into the background, and I'll walk you through the design strategy that we follow, and then we'll look at the drill and blast design processes that we follow there at Sky. And I'll give you one or two case studies of some of the blasts that we've had there and the lessons we've learned. And I'll just leave some time at the end for any questions or comments that you might have. Okay, just as an introduction, this is SkyChrome Mine. You can see just how the reef dips and just how challenging the operation is there. I've found myself falling on those benches a few times. It's not really the best place to work in, but it's challenging, but it's exciting as well. Just to introduce myself, my name is Kgothatso Rampou. I am proudly South African. I'm a proudly South African miner. I'm also a blasting magician in the making. And I'm also a proud husband and a father to a 6-year-old baby girl who is the absolute joy of my life. But that's enough about me. Just to introduce some of the key players at SkyChrome. First, we have ASB Minerals, which is a level 1 triple BE mining and construction services company in Southern Africa. They offer full contract mining services for both surface and underground mining operations. The management team at ASB has extensive experience in contract mining within the drilling and blasting domain. ERG Industrial is a global goods and services provider. We currently serve a customer base spanning over 65 countries worldwide. We have products all focused on producing value within the drill and blasting domain. And our engineering consulting services are predominantly aimed at creating sustainable value within the drilling and blasting space. Just to introduce some of the stakeholders at SkyChrome Mine. At the top, we have Samancor. They are essentially the mine rights holders at SkyChrome. Then we have ASB Minerals, that is the contracting company there. Then we have Butse Drill and Blast, they're in charge of the drilling and blasting operations at SkyChrome. Then we have ERG Industrial, we are in charge of all the blast designs and the timing designs. And then we have BMC, Blast Management and Consulting. They employ their seismographs, and that's what we use to track those nuisance factors. Then we have the Department of Mineral Resources and Energy, and we have the community of Papong in the northwest. That is the community in which these operations happen at SkyChrome. And just to give you an appreciation of just how close the operation is to the community, that is SkyChrome Mine, and next to it is the community of Papong. We conduct blasts as close as 100 meters in some cases to the structures, and so it is a really difficult site to work in, but it's also really exciting to be a part of. Just to get into the background, we follow the drill and blast value chain that we follow. It's split into 4 tiers. The first is the design inputs and considerations, so obviously your dates at the beginning. Then we go into the drill and blast design process that we follow. Then we go on into the execution, and then we do our post-blast analysis, which was very important. I heard somebody mention it earlier, just very important, the post-blast of, reporting on your post-blast, how important that is for continuous improvement. But the first things first is always to define your blasting objectives. For every site, the blasting objectives are different. And just to give you examples of different blasting objectives, this is a manganese mine in the Northern Cape in which their primary blasting objective is fragmentation. Specifically, they are trying to ensure that they get more lumps than fines. And so the primary blasting objective in this case is fragmentation. There's a coal mine in South Africa where the primary objective is ensuring that that nuisance factor, that is air blast, is kept within the allowable legal limit. And this is an operation in the UK. You can see just how bright and orange they look. It must say something about safety there in the UK. I don't know how safe it is, but you know, they're very visible. But also another example of fragmentation as a primary blasting objective, trying to ensure that they fall within that critical zone that is outlined there. And another example of fragmentation as a key blasting objective, in which they're trying to ensure that the particle size falls between the blue and the orange line that you see there in your graph. And so what is the key primary blasting objective at SkyChrome? The primary objective is to keep nuisance factors below the allowable legal limits. I'm sure some of you are wondering, what is this term, nuisance factors? Well, again, this is a term that was coined by our friend Tom from Gears, which essentially speaks on the unwanted factors that we get from blasting operations, such as your ground vibration, your air blast, and your fly rock. And so the primary objective of SkyChrome is to keep those within the allowable legal limits. And these are, to do that, we follow the guidelines as outlined by the Department of Mineral Resources and Energy. I know Thomas again earlier was talking about how outdated these are, but look, we managed to follow them and we still are able to blast, and that says a lot about us as well, hey? But yes, these are the guidelines that we follow in terms of like ground vibration and air blast. And secondary to that is to get fragmentation as good as possible. So to go into the design strategy that we follow a scientific, predictive, iterative, data-driven drill and blast design process. I know that sounds like a lot of fancy words, but that is exactly what we do. And in order to do that, there's a few technical levers that we pull. And the first one is the maximum instantaneous charge, or basically the amount of explosives that go off within a point in time. And to do that, we employ single hole firing, ensuring that we don't have two or more holes going off at the same time. And then we have our stemming plugs. If you look on your tables there, you have examples of your stemming plugs. I see some BP 3.5s there. But basically, that's one of the tools that we use, an optimization tool. It doesn't replace your design. Your design still has to be on point. That is very helpful in ensuring that we are able to blast in these sensitive areas. And then we also do a line drilling pre-splitting hybrid. As you know, pre-splits create a lot of energy. With a place like SkyChrome, we need to ensure that we are below allowable legal limits at all times. And to do that, we use a line drill pre-split hybrid, in which we essentially drill like you would with a pre-split, but then would charge one, leave one at a 50% charge, and we ensure that we stem all the holes in your backline to protect your high wall. But the biggest thing is going back to the basics. So that is essentially ensuring that the gap between the design and the actual is as small as possible. And then service delivery and communication. So essentially that is the design strategy that we follow. We'll go into the drill and blast design process that we follow at SkyChrome. I'll just give you a high-level overview of the process that we follow. We follow a stage-based approach. The first point is data acquisition. The data that you get has to be on point. If your data is incorrect, the downstream effects are terrible. And so your input files are very important. So the first thing will be to check if the data is correct. If the data is incorrect, then you have to go back. Get the correct data in order for you to start your design. Then we go over to our theoretical designs. We'll look at different hole, diameter hole configurations. We'll do our modeling using Open Blast. That is essentially the software that we use for our designs. And then from there, we'll look at the nuisance factors. Are we compliant with our nuisance factors? And if you're not, we go back to the theoretical design. That speaks to the iterative nature of the design process that I spoke about earlier. And you have to go back. If the nuisance factors are not compliant, we have to go back. If they are, then we move on. Once we're happy with our theoretical design, then we can produce a drill plan. That drill plan is now taken to the ground, and the drilling can now commence. Once the drilling is done, then we get the as-drilled data. We're not disillusioned enough to believe that what we design theoretically is what's going to be on the ground. And so you have to work with as-drilled data, and drilling QAQC is a massive part of that. And once we have the as-drilled data, we then are able to produce an as-drilled design. With the as-drilled design, we then check again what are the nuisance factors and what is our compliance. If we're not compliant with our nuisance factors, then we go back again. We look at our as-drilled designs, what we can change in order for us to ensure that we are within the allowable legal limits. Then we continue on to produce a charge plan. That's your charge instructions and our timing designs. And from then on, priming and charging can then begin. Then once the charging is done, then the charging QAQC is done as well. And we need to ensure that the charging passes independent charging quality checks. And if not, if we have undercharged holes or overcharged holes, then these need to be corrected before we can move over. Once that is done, then we get to our final stemming and tying up. Once the stemming and tying up is done, then we can have our blast event. Now, once the blast event is done, then we'll obviously have our drones up where we will be able to capture our blast. We'll have a blast video, and BMC will give us the readings on the nuisance factors using the seismographs. And then we are able to then do a post-blast analysis, looking at the visuals and looking at the readings that have been produced from the blast. With that, then we are able to give the post-blast report to the client. So essentially, this is the high-level overview of the drill and blast process that we follow at SkyChrome. And as you can see, it's very iterative, and it literally ticks all the boxes that I had mentioned in the drill and blast strategy that we follow. So just to give you some examples, this is an MG2C overburden blast that we did at SkyChrome. If you look on your left there, that is an example of the blast radius plan that we have there. And that is where all the seismographs have been placed. You can see the distances as well. And I think in this case, the closest structure was 129 meters away, with the ground vibration limit of 12.5 millimeters per second. With those input files that I spoke about at the beginning to create a theoretical design, we then are able to use the topo that we have, the reef data that we have, to produce a theoretical design. And that's just a typical example of the theoretical design for this one. This is for the MG2C blast. And from then on, with the same open file design software, we then are able to produce these rings that essentially show you what the blast radius is, but most importantly, at distant intervals, I think in this case it's 10-meter intervals, we are able to see what the predicted PPVs are. We can use our rule of thumb laws, but over time we've managed to build a database enough to create a site-specific law that allows us to get very close to the actuals. And with the theoretical designs, we look at 3 different designs. This is a 115 diameter design, 102 and an 89, and in this case all of them were within allowable legal limits in terms of ground vibration and air blast. That allows us then to tap into the secondary objective, that is fragmentation, and we can look at which design is the optimal one depending on the needs. And this is just an example of the schematics that we produce of the different charging configurations that we have. For the buffers there, we have for the production holes, and then we have for our line drills, that charge one, leave one example that I gave earlier. And that essentially covers this first section of our drill and blast design process. That was for the MG2C blast. We got our data and we were able to produce a theoretical design. So the rest of the process, if you look in this case, these are basically our blast parameters that we had. The hole depth theoretically was at plus minus 9.6 meters, and we had planned to blast 819 holes, and the as-drilled data came back. Again, just to know how important the as-drilled data is, you see now the hole depth, we were now averaging 9.2 meters, with the maximum hole depth at 10.7 meters after the drilling QAQC, and only 525 holes were drilled. And in actual fact, before the blast went off, after the charging was done, only 502 holes could be charged. Again, changes happen on the field. There might have been holes that were shorter, or holes that had ingress of water, or like collapsed holes. There's a lot of reasons in which holes cannot be charged, or some holes are only primed only. But essentially only 502 holes were charged in the end. And these were essentially the results that we got from that specific blast. For our air blast, we had theoretically predicted those values there, the as-drilled predictions, and you can see the actuals on the right. For the vibration as well, you can see what our theoretical predictions were and what our as-drilled predictions were, and the actual measurements. You can see just how close our actuals were to our predictions, and that again is thanks to the site-specific attenuation laws that we are able to build over time with the blasting at Skychrome. So the first blast at Skychrome was fired in January of 2025. The process started in August of 2024. If you look to your left, those are all the blasts that we've had to date, and we have had 100% success in keeping nuisance factors below allowable legal limits. Thank you very much. That's all me. And secondary to that is getting fragmentation as good as possible. We keep blasting, so must be good. Just some eye candy. I'll just give you a visual of the same MG2C blast. Just have a look. As you can see, another really boring blast. Corey, like, this is how you blast, not that police blasting that you showed us earlier. But essentially, we are in the business of producing boring blasts, and that's just a video of that same blast. Okay. And now we'll go into the lessons that we have learned from working at Skychrome. The first one is data integrity. All spatial and geotechnical input files are independently verified before the design commences. We can't stress enough just how important your input files, your data is at the beginning before you start with your designs, because errors propagate through every downstream calculation. The multi-design iteration, evaluating 3 or more diameter configurations before selecting a final design, ensures the optimal balance of fragmentation, vibration, and cost is achieved. Timing optimization, single hole firing confirmation via histogram analysis with fixed normal delay intervals is essential to limiting effective charge per delay and in controlling ground vibration. QAQC rigor. Charging instructions must reflect verified astral depths and not theoretical values. And so your QAQC is extremely important, both your drilling and your charging. Unverified depth data introduces charge per delay errors that directly affect your ground vibration outcomes. And next, field supervision. Physical presence of the blast engineer during loading and firing is a non-negotiable safeguard. Don't be a bucky blaster. I can see from some of you that are smiling here that there's a few bucky blasters here. But field conditions routinely diverge from design assumptions. So you need to be down on the field, see what the changes are, and those need to be recorded and shared with the team so that they can, if there's any changes that need to be made, they need to be made before the blast goes off. Continuous monitoring. At Skychrome, we have 7 station seismographs that cover the nuisance factors. These records enables both real-time compliance verification and long-term attenuation model refinement. Stakeholder communication. Transparent, consistent pre-blast notification and post-event reporting to all affected parties sustains project social acceptability and reduces complaint frequency. And I must